When adding and subtracting radicals, the same goes for square roots as any other roots. They have to be like terms. So you couldn't add before, like the square root of 20 plus the square root of 5, because they weren't the same number underneath that root. The same thing goes for higher root radicals. So when you're trying to add and subtract these, you want to look at what is behind your coefficient. So for number 12, the first term there has a coefficient of 7. The second term has a coefficient of 1. What is attached to that coefficient has to be exactly the same. Same radical index, same number underneath the radical. So in this case, they are exactly the same, so we can go ahead and subtract them right away. So 7 minus 1 would be 6 fifth root 12s. We're just kind of saying how many fifth root of 12s do we have. But you can't add and subtract them unless they're exactly the same. So let's see here. Let's look at number 14. So this one, they're both the cubed root, but it's the cubed root of 81 minus the cubed root of 24. So they are not alike, so we need to simplify them. And after we've done that, hopefully they should be the same. So let's see. 81 could be 9 and 9. So we've got a cube root, so we need a group of 3 things, and then that guy's left by himself. So 3 cubed root 3 is the first term, cube root of 81. Bring down your minus sign. And then 24, 12 and 2, 6 and 4, 8 and 3, whatever you guys want to start with. So again, a cubed root, so a group of 3 things is what will go outside, and a cubed root of 3, which is perfect because that's what we had in the first term we simplify. So now we've got 3 cubed root 3 is minus 2 cubed root 3s. So how many cubed root 3s do we have? 1. Okay, so let's look at 13. Adding into the many exponent rules that we already know, we need to add one more. Along with your negative exponents, we don't want fraction exponents. So, sort of like when you guys are simplifying and as soon as you see a negative exponent, you just kind of move it to make it positive. I could sort of similarly do the same thing when I see fraction exponents. If I can't have a fraction exponent, we know how to rewrite this in root form. It would be the cubed root of 9 squared. So we could then say, since both roots are the same behind the 7 and the 4, how many cubed root of 9 squareds do we have? 11. But 9 squared, we would want to make sure we can't simplify that because we know 9 squared to be 81, correct? So if we factored that just to make sure it was simplified, we would see that there actually is a perfect third root in there. It's 27. 27 times 3. So the final answer would actually be 11 times 3 on the outside. And cubed root of 3 left. But we don't want to leave our answer with a negative exponent or a fraction exponent. So similarly, 22, I'm going to rewrite b in 2/3, or b to the 2/3. So 15 a to the 4th cubed root b squared plus 8 a to the 4th cubed root b squared. So it seems kind of weird, I think, because we have so much stuff behind those coefficients now than what we used to, kind of. But it's still the same idea. We're saying how many, as long as they're the same, a to the fourth times cubed root b squared do we have? 15 plus 8 of them, 23. Just keep what was behind it, or attached to it, if you will. Okay, so how about 23? They are nothing alike. We have 10 as the coefficient, and then the fourth root of 5s to the 7th. 1 as the coefficient for the second one, and then s times the fourth root of 80s cubed for the second part. So what should happen is after we're done simplifying these, again, they should be alike, but we just do it one at a time. So almost ignore that this one is over here for right now, and just simplify this first one. So you can't take the fourth root of 5 at all. So he is just going to stay underneath there. But how about the fourth root of s to the 7th? How many times does 4 go into 7? Once. And then 3 remaining. So the 10 was just out there. We couldn't take the fourth root of 5. So the only thing we really did here was simplify the fourth root of s to the 7th. That's all we did. The 10 was still there. The 5 stayed there. All we did was simplify the s's. So let's look at the second one. We can bring down our subtraction sign. So the fourth root of 80. There's probably going to be a fourth root in there. So let's factor that guy. 10 times 8, 4 times 2, 2 times 2, 2 times 5. So we don't want to include any of those guys that aren't prime. So we need a group of 4 things that are the same to make that perfect fourth root. So we have a group of 4 2's, and the 5 is left. So that 2 is going to come out with that s. 5 is left. Okay. How about s to the third? Does 4 go into s to the third? No. It's going to stay. We also kind of knew that because we needed s to the third to match in there. But now, what's behind the 10 and the 2 is exactly the same. S to the first times fourth root 5s cubed. So, a little weird, but how many s to the first times the fourth root of 5s cubed do we have? 10 minus 2, 8. So just take it one piece at a time, simplify one term at a time, and afterwards, after you're done simplifying, they should be the same. If they're not the same, you can't add or subtract them together. So if we're asking you to add or subtract the terms on a test or a quiz, expect that after you're done, they should be alike. So if they're not, we need to go back and check something to see what went wrong there.